In this video, we're going to learn how to solve applied problems involving hyperbolas. Hyperbolas are found in many applications in science and engineering. One example of an application can be observed in the use of hyperbolic mirrors in large telescopes used for deep space observations. In this image shown here, we have a case-grain telescope which uses a primary parabolic mirror to reflect incoming light to a hyperbolic secondary mirror, which then directs the light towards the viewer. Another example is in structural engineering, such as the design of natural draft cooling towers used by power plants, as shown in this image. The cooling towers are in the shape of a hyperboloid, a solid obtained by rotating a hyperbola about its conjugate axis. Hyperbolas are also used in audio detection. In this image, we have three microphones placed in a plane that are located at points O sub 1, O sub 2, and O sub 3. O sub 1 and O sub 3 are the foci of one hyperbola shown in the color blue. O sub 1 and O sub 2 are the foci of a second hyperbola shown in the color black. O sub 1 is a shared focus between both hyperbola. A point labeled S is also plotted. S lies on the graphs of both hyperbolas. It lies on the branch of the blue hyperbola with focus O sub 1 and on the branch of the black hyperbola with focus O sub 2. Suppose that a gun is fired at point S and the microphone at O sub 1 records the gunshot 1 second after the microphone at O sub 2 hears the gunshot. Now, because sound travels at 1100 feet per second, we conclude that the microphone at O sub 1 is 1100 feet farther from the gunshot than O sub 2. And note that the difference in the distances from S to O sub 1 and S to O sub 2 is the constant 1100 feet that would be referenced in the definition of the black hyperbola. If the third microphone at O sub 3 records the gunshot 2 seconds after O sub 1, then S lies on a branch of a second hyperbola with foci at O sub 1 and O sub 3. And in this case, the constant difference will be 2200. The intersection of the two hyperbolas identifies the location of S. In this example, we consider the sound heard by two people who are watching a rocket. The problem states, suppose that two people standing 2 miles apart both watch the launch of a rocket. After a period of time, the first person, standing at point A, hears the roar of the engines observed from the initial firing of the rocket engines. 2 seconds later, the second person, standing at point B, hears the roar. If the person at point B is due west of the person at point A, and if the launch is known to occur due north of the person at point A, where did the launch occur? Let's begin by visualizing this scenario by sketching an X and Y axes. Next, let's denote the positive Y-axis as representing the direction north, the positive X-axis as representing east, the negative Y-axis representing south, and the negative X-axis representing west. Let's orient the hyperbola so that the center is at the origin and the transverse axis is the X-axis. We begin by placing point A on the positive X-axis. This point represents the person standing at the focus who is the first person to hear the roar of the engines. Then let's place point B on the negative X-axis so that it is due west of point A and represents the other focus of the hyperbola, which is the location of the person who hears the roar after the person at point A. Next, let's plot the two vertices at the points A, 0, and at the point negative A, 0. Then let's sketch the branches of the hyperbola opening to the right and to the left. Now let's plot the rocket at the point X, Y on the right branch of the hyperbola. Now this point is due north of point A, therefore it lies in quadrant 1. Let's also sketch a dotted line connecting point A to the point X, Y and from point B to the point X, Y. Now lastly, let's denote on our diagram that the distance between points A and B is 2 miles. Since we oriented the hyperbola so that the center is the origin and the x-axis is the transverse axis, then the general equation has the form x squared divided by a squared minus y squared divided by b squared equals 1. And in order to find the equation, we need the values of a squared and b squared. So to determine a, we use the fact that the person standing at point B heard the roar 2 seconds after the person at point A. Now, since the speed of sound is 1100 feet per second, then after 2 seconds, the sound has traveled 2200 feet. Therefore, the person at point A is 2200 feet closer to the rocket. In other words, the difference in distances from A to the rocket and from B to the rocket is 2200 feet. Now recall, by definition, this distance is constant for any point on the hyperbola and is equal to the length of the transverse axis, the distance between both vertices. So we can write the equation 2a equals 2200. Dividing both sides by 2, we find that a is equal to 1100 feet. And now we need to find b squared. For hyperbola, we know that b squared is equal to c squared minus a squared. We need to determine the value of c so we can calculate b squared. To determine the value of c, we are told that the two people standing at the foci are 2 miles apart. We know that 1 mile is equivalent to 5,280 feet, so we can write an equation 2c is equal to 2 times 5,280. Dividing both sides by 2 gives us c equals 5,280 feet. So now that we know the value of c, let's go ahead and label the coordinates of the points A and B. So point A is located in the xy plane as 5,280, 0, and point B is located with coordinates negative 5,280, 0. So again, now that we have c, let's go ahead and find b squared. So b squared is c squared minus a squared. This is going to equal 5,280 squared minus 1,100 squared, which equals 26,668,400 feet. Now, since we now have the values of a squared and b squared, we can write the equation of our hyperbola as x squared divided by 1,100 squared minus y squared divided by 26,668,400 equals 1. Now that we have the equation of the hyperbola, then we can answer the question in the problem statement, which is find the location of the rocket. In order to accomplish this, we will substitute x equals 5,280 into the equation to find the y coordinate of the point we labeled as x, y that represents the rocket and is due north of the point A. Now, substituting into the equation, we can write 5,280 squared divided by 1,100 squared minus y squared divided by 26,668,400 equals 1. Subtracting 5,280 squared divided by 1,100 squared from both sides of the equation, we have negative of y squared divided by 26,668,400 equals negative 22.04. So now multiplying both sides of the equation by negative 26,668,400, we have y squared equals 587,771,536. Therefore, y equals 24,244 feet. And we take the positive square root since the rocket lies in quadrant 1. So the rocket was launched 24,244 feet north of the person standing at point A. Even though we weren't asked if we wanted to determine the distance in miles, we would divide our answer by 5,280 feet, and we would get that y is approximately 4.59 miles due north of the person at point A. Well, let's take a moment and check our work. Let's write the coordinates of the rocket as the point P equals 5,280, 24,244. Now, one focus at point B has coordinates negative 5,280, 0, and the other focus at point A has coordinates 5,280, 0. Now, by definition, we know the difference of the distances from the foci to point P is the constant 2200. We can write this as the distance from P to B minus the distance from P to A equals 2200. Now, using the distance formula, we can calculate the distance from P to B as square root of the quantity. Now, under the square root, we're going to have the square of the difference in the x-coordinates plus the square of the difference in the y-coordinates. So the difference in the x-coordinates is 5,280 minus negative 5,280, and this is all squared. Then we add to that the square of the difference of the y values, which we would get 24,244 minus 0, all squared. Now we need to subtract from that the distance from P to A. Now again, using the distance formula, this is the square root of the quantity. The difference of the x-coordinates will be 5,280 minus 5,280, all squared. And then we add to that the difference in the y-coordinates, which would be 24,244 minus 0, all squared. Using a calculator to help us manage these really large numbers, this turns out to be 26,444 minus 24,244, which equals 2,200. Therefore, we have found the correct location of the rocket, since this point does lie on the hyperbola, satisfying the definition.